on page 203. So always start at the same place. Identify whether you're working with an individual element, a compound, or a polyatomic for the assigning purposes. So KClO3 is a compound, and likewise NH4NO3 is also a compound. So when you're working with a compound, the sum of those oxidation numbers must, in the end, sum up to 0. So I'm going to start with the KClO3. So like all the others, I'm just going to do a little reverse engineering in my thought process. So I have 1K that I have to add its charge to 1 chlorine, but I also have to add those charges to 3 oxygens. So when I have a formula that's made up of 3 different elements, I like to first assign to the outside and then save the middle one for the end. So when I open up my periodic table, I see that K comes from group 1. Group 1, cations, we assign a +1 charge. I also notice that this contains oxygen. It doesn't end in O2, it's not a peroxide. Oxygen's not bonded to fluorine, so I know that this is just common oxygen, which assigns it a -2 charge. So when I add up these charges that I have figured out so far, okay, the sum needs to equal 0. The 1 potassium supplies a +1 charge. Chlorine will make up the difference. The 3 oxygens each use a -2, so collectively they supply -6. -6 plus a +1 leaves me with a -5. Chlorine needs to supply enough charge to cancel out a -5. So that means that the chlorine must be using a +5 charge. So total -6 plus a +5 plus a +1 sums to 0. Now this last example, what makes it maybe a little bit tricky is that this example, this compound is made up of 2 different polyatomics. So one polyatomic is NH4 and the other one is NO3. You can find both of those on your table E. So this one, I work with it a little bit differently. So I know that the polyatomic NH4, according to table E, uses a +1 charge. And when I add it to the polyatomic unit, NO3, and according to our table E, the NO3 uses a -1. So the +1 from the ammonium plus the -1 from the nitrate, it sums to 0. The little bit of a trick here, or what's new, is that this nitrogen in the NH4 and the nitrogen in the nitrate, they actually use different oxidation states, and that's what we have to figure out. So I'm going to solve this in this manner. So I'm going to first focus on ammonium. So in ammonium, I have 1 nitrogen, and it is bonded to 4 hydrogens. And when I add up their assigned charges, I'm going to use their assigned charge of +1. Okay, so here I have a hydrogen, and that hydrogen is bonded to a nonmetal. So my 4 hydrogens are each assigned a +1. So 4 hydrogens contribute a +4 charge to the ammonium. Whatever I assign to ammonium, whatever I add to the +4, the sum needs to be a +1 total. So I'm not canceling out the +4, I need a +1 left over. So that means I'm going to assign the nitrogen in ammonium a -3. So -3 plus a cumulative +4 gets me to a +1. So the nitrogen in ammonium uses a -3, the hydrogens use a +4. Now I'm going to solve the nitrate one in a similar manner. So I have 1 nitrogen in that unit, and it is bonded to 3 different oxygens. And when I add their charges together, it needs to add up to their shared charge of -1. So I notice in this formula that I have oxygen in this polyatomic. It doesn't end in O2, not a peroxide. The O is not bonded to fluorine, so this is common oxygen. I assign it a -2 charge. But there's 3 of them, so collectively they contribute a -6. Whatever I assign to nitrogen, the only nitrogen in this poly, it supplies enough charge that when I add it to -6, the sum is a -1. So this nitrogen in the NO3, it will be using a +5. So sometimes you just have to work through it and apply some different ideas to figure out your assigning oxidation numbers.